In the vast, silent darkness between the stars, a cosmic drama unfolds. A massive star, once a radiant beacon burning with unimaginable intensity, reaches the end of its nuclear life. For millions of years it held itself steady, its fusion-powered heart pushing outward against the crushing weight of gravity. But nothing lasts forever. When its fuel finally runs out, the balance collapses. In moments, gravity wins. The star's core implodes, shrinking from something larger than our sun to something smaller than a city. Temperatures soar, pressure skyrockets, and nature reveals one of its most violent transformations. Under these catastrophic forces, atoms crushed into neutrons begin to yield, their subatomic structure shattered. What was once the heart of a star becomes a point of pure collapse. Then, as the dying giant violently explodes outward in a supernova, its core continues to fall inward, deeper and deeper, until space-time itself yields. A boundary forms, a horizon beyond which no light escapes. The star is gone, replaced by something far more mysterious. A black hole is born, and at its center lies a question so profound, so unsettling, that even our greatest theories fall silent before it. The event horizon is the most misunderstood place in the cosmos. It is not a surface, not a structure, not a wall. It is simply the line where escape becomes impossible. On one side, light can still flee to the stars. On the other, even photons are caught in a gravitational current too strong to resist. But to the outside observer, this boundary is a spectacle of distortion. Time behaves strangely. Objects falling and appear to slow, caught in an eternal descent that never seems to complete. Light stretching outward reddens until it fades into invisibility. The black hole seems to swallow objects in slow motion, not because time stops, but because the fabric of time is warped into something unrecognizable. Crossing the horizon is different. Inside, there is no turning back, no reversing course. The direction of inward is no longer a choice. It becomes a destiny written into space-time itself. The closer one draws to the center, the faster the descent becomes, not by motion alone, but by the geometry of reality tightening like a funnel. Yet for all its terrifying simplicity, the horizon is merely the beginning. Beyond it lies a realm where physics enters uncharted territory. Inside the event horizon, gravity becomes not a force, but the very shape of the universe. Space narrows into a single, unavoidable direction, and time ceases to flow as it once did. The familiar separation between space and time dissolves. Here, the future is inward. The center is not a location, but a moment, one every falling object must reach. Tidal forces intensify with catastrophic speed. As the gravitational gradient sharpens, objects stretch along the direction of the fall while being squeezed from the sides. Spaghettification, an unsettling term, captures the horror of this process. But while the name sounds whimsical, its implications are not. No structure, no matter how strong, can resist this stretching. Molecules, atoms, even subatomic particles feel the strain. Yet the descent is not chaotic. There is symmetry to it, a strange calm hidden behind the violence. The path toward the core is inevitable, carved by Einstein's equations with mathematical precision. The singularity is not a thing that pulls, it is the end of the path, the destination encoded into the geometry of collapsed space-time. But what is the singularity? Even today, the question remains unanswered. The singularity lies at the conceptual heart of a black hole. In the classical view of general relativity, It is the place where density becomes infinite, where the curvature of space-time grows without limit, and where the laws that describe gravity simply fail. But infinity is often a sign not of truth, but of mathematical breakdown, an indication that the equations are being pushed beyond their domain. If the singularity were truly a point of infinite density, it would represent a region where matter has been compressed into an impossibly tiny volume, where space itself ceases to exist in any meaningful way. But such a place defies everything we know about quantum physics, which insists that particles cannot be pinned to infinitely small points. So what truly lies at the center? Einstein's theory predicts collapse. Quantum theory says no. The two foundations of modern physics clash, leaving a void in our understanding. Some believe the singularity is not a literal point, but a placeholder, a sign that a deeper theory waits to be discovered. A theory that unites the cosmic and the subatomic, the vast and the tiny. A theory of quantum gravity. Until then, the singularity is not a place we understand. It is the edge of our knowledge. When gravity grows extreme, quantum rules rise to the foreground. In these depths, particles and probability blur. Time and space vibrate with uncertainty. It is here that ideas once thought speculative take on new plausibility. One idea proposes that matter never reaches a true singularity. Instead, quantum pressure halts the collapse, forming a Planck-sized core, small beyond comprehension, yet not infinitely so. Another idea suggests rotating black holes contain ring singularities, structures where space-time bends into loops, allowing for pathways that twist in directions we cannot visualize. In these warped geographies, time may circle back on itself. Causality may bend. Some theories take us further still. Black holes may be gateways, wormholes that connect distant points in space-time. Or they may be cosmic seeds, with each singularity birthing a new universe within. In this picture, our entire cosmos could lie inside the event horizon of a black hole in another universe, a chain of nested realities stretching without end. Then there is loop quantum gravity, suggesting that collapse leads to a bounce, a rebirth. Instead of ending in a singularity, matter might rebound, creating an expanding region of space-time sealed behind the horizon. These are not fantasies. They are possibilities born from the clash of physics' greatest theories. Despite our best tools, black holes keep their secrets locked behind horizons that no telescope can penetrate. Even the Event Horizon Telescope, which gave us the first image of a black hole shadow, can only show the imprint of the hole on surrounding matter, not the interior, not the core. Gravitational waves reveal the structure of collisions, the way black holes merge and deform space-time, but they cannot pierce the horizon. Light is trapped. Signals are lost. All information that crosses the threshold disappears from the universe we know. Thus, the center of a black hole remains hidden behind the ultimate veil, beyond reach, beyond testing, beyond direct observation. It is a reminder that science, for all its triumphs, still faces boundaries drawn by nature itself. Yet those boundaries are not dead ends. They are invitations. So what lies at the center of a black hole? A singularity of infinite density? A quantum core governed by laws not yet written? A ring, a bounce, a portal, a seed of a universe? Or something stranger still, something we lack even the language to describe? The answer remains shrouded behind the horizon. We cannot see it. We cannot measure it. But the mystery itself drives us forward. It pushes us to refine our theories, to expand our imagination, to deepen our curiosity. Black holes are not merely cosmic abysses. They are reminders that the universe still contains secrets big enough to challenge our greatest minds.